Welcome back, Baby's kids. Time to talk about similarity. There's a lot of information here. This might be one of the longer videos. I'm going to go through pretty much every similarity situation that will face this chapter. There'll be one or two that we'll do later, but this pretty much covers all the basic properties for the whole unit. So a lot to learn here, a lot to dig into. Of course, rewind, fast forward, go to the parts you need to hear. But there's a lot here. First off, what is similarity? At its most basic level, similarity means you have the same shape, but they're different sizes. What determines the shape? What determines what it looks like? Well, that's the angles. So if the angles match, you know that they're the same shape. This is determined by angles. We talked about this with congruency as well. This is determined by the sides. So these must be equal. The sides are not going to be equal, but they are going to be proportional. And we'll talk about that more in a second. So same shape, different sizes. Those are going to be similar shapes. All right, let's talk about here. Different formats for writing a ratio. All three of these represent the same thing. I don't know if you knew that or not, but they do. And they're all just as, doesn't matter which one you really use. But something we need to know about is something called an extended ratio. So this builds on this. Which one of these formats do you think would best be suited for an extended ratio? Well, an extended ratio compares more than two things. Like right now we're comparing two things, right? 16 ducks and 9 geese. An extended ratio would be comparing more than two. For example, if I told you that the angles of a triangle have a ratio of 1 to 3 to 5. Okay, if that's what I told you, and I said, how big were the original angles? That is an extended ratio. That is this format. That's the best one to use. You wouldn't want to write that as a fraction. 1 to 3 to 5, no thank you. No thank you, that doesn't make a lot of sense. So how do I figure out what were the original sizes? So basically what we're doing is we need to unreduce this ratio, right? So let's backtrack a little bit. What would you do if I said, hey guys, we have the angles of a triangle and they're 50, 60, and 70 degrees. And I said, write that as a ratio. Well, you would write that as 50 to 60 to 70. But then in order for it to be fully simplified, you would have to reduce. How do you reduce 50, 60, and 70? You divide by 10. So you would reduce it to 5 to 6 to 7. Right? So how do we unreduce it? Well, if you divide by 10 to reduce it, wouldn't you just multiply it by 10 again to unreduce it? You would do 5 times 10. You would do 6 times 10, and you would do 7 times 10. Wouldn't that give you the original numbers? Yes. The issue is we don't know what we reduced by, right? We know that the ratio is 1, 3, and 5, but we don't know what they reduced by. So what we do is we multiply it by x. Why x? Because we don't know the number. So we're going to call the factor that we reduce by x. Well, 1 times x is just x, 3 times x, and 5 times x. Right? We know it's the same number all 3 times, right? It was 5 times 10, 6 times 10, 7 times 10. So it's the same number every time. We're going to call it x. And we know that if we add those original numbers, that they have to add up to 180. The original angles of a triangle have to add up to 180. So we know this must be true. Well, that would be 9x has to be 180, so x has to be 20. That means that our original sizes are 20, 3 times 20 is 60, 5 times 20 is 100. Those are the original angles of the triangle. This was the factor that they reduced by, so we multiply that back in, boom. We're going to circle back to that later. We're going to use a lot of proportions, so we have to understand a few things. There are 4 ways to write every proportion. I'm going to go through these real quick, but 1/2 equals 5 over 10. That's true, right? What is 5/10? If I reduce that, isn't that 1/2? So yes, this is true. But what's another way to verify that it's true before we move on? Something that you've learned before, but you may not have realized, is that if the cross products are equal, 10 times 1 equals 5 times 2. Well, 10 equals 10, yes. If the cross products are equal, then the proportion is true. Like the ratios are the same ratio, I should say. So we know that 1/2 and 5/10 are the same thing. We know it because we could reduce it and they both equal 1/2. We also know it because of the cross products. Something we need to know, though, is how else can we write this? We could also write this as 1/5. If I said 1 over 5, that would have to go with 2 over 10. That is left over right equals left over right. I could also do 5 over 1 equals 10 over 2. That would be right. That would be right over left equals right over left. I could also do 2 over 1 equals 10 over 5. That would be bottom over top equals bottom over top. So there's a total of 4 ways to write every proportion, and all 4 of these are true, right? Isn't 1/5 the same as 2/10? Isn't 5 divided by 1, 10 divided by 2? These are all the same thing. How do I confirm? How do you know that these are all the same proportion? It's with the cross products. 1, 10, look at every single cross product. 1 and 10, 2 and 5. 1 and 10, 2 and 5. 1 and 10, 2 and 5. Every single one of those cross products is 1 and 10, 2 and 5. So this is the same proportion written 4 different ways. So anytime you want to know, hey, is my proportion the same one as someone else's? Check the cross products. If your cross products are the same, your proportions are the same. And a very important thing to note here is when you have a proportion, you can reduce vertically and horizontally. Why? Isn't there a version of this proportion where 2 is over 10? Yeah, there is. That means you can actually reduce this way. That would become 1 and 5. Well, isn't that still true? 1 divided by 1, doesn't that equal 5 divided by 5? Yes. So keep that in mind. We're going to look at that here in a second. So how would we write all the different versions of this one? This would be x over 5 would equal 7 over 15. You could say 5 over x equals 15 over 7. And you could say 7 over x equals 15 over 5. There's all the versions of that one. How can we solve this without cross multiplying? Bonus, solve without cross multiplying. Well, if you look at this, doesn't this reduce to 1/3? So what does this ratio have to be? It has to be 1 to 3. In other words, it's 5 times 3 equals 15. So 8 times 3 has to equal 24. A big deal with proportions is staying consistent. As long as you keep doing the same stuff, there's a great chance you're doing it right. So over here, to go from top to bottom, how do you go from 5 to 15? You do times 3. So yeah, that's what you have to do over here as well. All right, how would you solve these equations? And I want you to get used to this. This is a big deal. We must reduce first. You're going to have portions without a calculator, and if you don't reduce first, this becomes very hard. For this problem, I want to make note of something people do wrong. They do stuff like 9 and 3 and call that 3 and 1. Doesn't work out that way. Sidebar, if I said 7 plus 2 divided by 7, can I cross out the 7s and say the answer's 2? Can I do that? No. Division does not undo addition. It doesn't work. You can't do that. 7 plus 2 divided by 7 does not equal 2. You would do 7 plus 2 is 9. That answer is 9/7. Now, if it was 7 times 2 divided by 7, could you just cross those out and say the answer is 2? Yes. Right? 7 times 2, 14, divided by 7, yes. That's because division undoes multiplication. It doesn't undo addition. So you cannot do that. No. But remember, we just talked about you can reduce vertically, but you can also reduce horizontally. 9 and 18, those do reduce to 1 and 2. And now we can cross multiply. Don't forget to distribute. That would be 2x plus 6. Go this way. That would be x plus 15. So you would know that x equals 9. Boom. Next one, I'm going to go a little quick, but same idea, 5 and 15. Okay, we reduce vertically, but we can also reduce horizontally, 1 and 15. right? 3 and 45 reduces, so we're just left with ones. So 15 times 1 would be 15 equals 2x plus 3 times 1. Well, that's just 2x plus 3. So 2x has to equal 12, x has to equal 6. Reduce, then cross multiply. If you don't do that, there's going to be some really hard questions. Reduce first vertically, then horizontally, then cross multiply. That's what you do. All right, next thing we got to know. How do we prove triangles are similar? There's 3 ways. Remember with congruency, there were 5 ways, but some of those ways are built in here. For instance, AA covers AAS, because let me start over again. If it's 2 A's, don't we know the third A is a match, right? Like if I have a 50 and a 60 and another triangle is a 50 and a 60, that's enough. That's AA. Why? What is the third angle in both cases? It's got to be 70. So 2 angles is enough. You already know they're similar. So do you need angle, angle, side? No. 2 angles is enough. Do you need angle, side, angle? No. 2 angles is enough. So 2 angles gets you similarity. So like here, if I have parallel lines, corresponding angles are equal. Corresponding angles are equal. The 2 triangles are similar, angle, angle. So we would say triangle CDB is similar. That squiggly means similar to triangle CEA. Angle, angle. Over here, side lengths. Now remember, sides are not equal. Sides are proportional. So like what would the 5 go with? 5 is the smallest side. It has to go with the smallest side, 10. 7 is in the middle, has to go with 14 in the middle. And then 10 is the biggest, has to go with 20 the biggest. All of these reduce to 1/2. So we could say SSS, side, side, side. The S means that they're all the same ratio. Remember that the sides have to be proportional. We also could have used SAS because we have vertical angles. So either one of those we could have used on this one. And how would we name it? We know that triangle JAM is similar. If I go J to A to M, I'm going small, right? J to A is small, medium, large. I need to do the same order. Small, medium, large. So how do I do small, medium, large? It would have to be triangle EAS. There's my similarity statement. But to prove triangle similar, it's got to be one of those 3 things. Moving on. Scale factor versus similarity ratio. This is a low priority. Knowing the difference, I should say, is a low priority. You have to know how to solve problems. But knowing the difference between scale factor and similarity ratio is a low priority thing. A lot of teachers don't understand it. It's not an easy concept. One of the big reasons is that the scale factor is a fluid thing. The scale factor changes depending on what you're trying to find. So there's a few ways to think about this, though. Scale factor, I think of it as being the new shape over the old shape. I think of it as being the shape I want divided by the shape I have. I think of it as being shape number 2 divided by shape number 1. Similarity ratio is the reciprocal of all those things. It's the old shape divided by the new shape. It's the shape I have divided by the shape I want. It's the first shape divided by the second shape. So they are reciprocals of each other, and they both have their different purpose. But that's pretty confusing. Most people don't even understand that. Here is the most simple way, I think, to explain scale factor. Scale factor is the number you multiply by. It is the number you multiply by to get what you want. Similarity ratio is what you use when you're setting up proportions. Okay, so if I said DE to AB is a ratio of 1 to 3, what does that mean? That means for every 1 unit on DE, I have 3 units on AB. That's what it means. Okay, so what would be the scale factor? Well, here they say DE is 12. How would you get this side using scale factor? I'm going to call it X. Scale factor is the one we want divided by the 1 we have. We want the 3. We have the 1. Remember, the ratio is 1 to 3. So the scale factor would be 3 in this particular case. But what about going the other way? So like on this one, I would do 12 times 3 and I would get 36. This would be 36 on that situation. But how about going the other way? I know this gets messy with multiple problems, but AB is 15. So this is a new problem. I'm going to say this side's 15, and I'm going to call this side Y. How do you go the other way? How do you go from the 3 back to the 1? What would you multiply by? You would multiply by 1/3. You would do 15 times 1/3 equals 5. So when solving in the brown scenario, the scale factor is 1/3, but in the green scenario, the scale factor is 3. It depends on what you want. It's a dynamic situation. That means it can change. It's not static. So depending on what you're looking for, the scale factor keeps changing. But scale factor is the number you multiply by to get what you want. Whereas a ratio is a little bit different. The bottom line is, can you solve the problem? So how would you solve these same problems with ratios? Okay, in the green situation, we know that it would be 12 over x, right? The one we have divided by the one we want. And that would equal a ratio of 1 to 3. Cross multiply, you get x equals 36. Same answer. So that's how you would solve that using ratios. How about the brown situation? How would you solve the brown situation using ratios? Well, you would do y over 15, and that would equal 1 over 3. So we could just use that 1 to 3 ratio both times. It's no big deal. Reduce, that'd be 1 and 5, so y would equal 5. You get the same answers. I'm not too worried. If you don't understand the difference between scale factor and similar ratio, I'm not too worried about it. I didn't even explain it fully because it's just not worth our time. Knowing how to solve the problems is the big deal. So let's take a look here. We got similar shapes. This is shape 1. This is shape 2. DE is 12. IJ is 8. HG is X. And BC is 9. You can use scale factor or ratios. I don't care. So I'm even going to kind of ignore this a little bit. Just how would you get X? Most people look at this, okay, and they're like, okay, I can do left over left equals right over right, and they're correct. Make sure you follow up with the name. Like that's IJ. Look at the name. What does IJ go with? DE. DE. It has to be in the correct spots in the name, and it is. So then you could reduce this. That would be 2/3. You can reduce the 3 and the 9. That would be 1/3. And you'd get x equals 9. And that's correct, and you're done. As long as you can do that, I'm happy. How would you do the same thing with scale factor? So scale factor means you need to know what the ratio is. If it's 8 to 12, isn't that a ratio of 2 to 3? So what would I multiply by to get x? 9 times what equals x? Well, it's not times 3 halves. If I did 9 times 3 halves, my number is getting bigger, but I know x has to be smaller. What would you have to multiply by to get smaller? You'd have to multiply by 2/3. Wait, I think I messed up on the last one because these are not the same answer. Oh, I sure did. Glad I did both ways. This would not be 9. Sorry, 3 times 2 would be 6. I was like, wait a second. I found it. So that would be 6. Over here, though, 9 divided by 3, that's 3. 3 times 2 is 6. So once you have, here's the thing, guys, and this is going to happen in a lot of problems. If you have one set of corresponding sides, you need to establish that as your similarity ratio. In this case, that is a ratio of 2 to 3. We know that shape 1 to 2 is a ratio of 2 to 3. So if I know that, like, let's just make up another number. Let's say that this top side was 10 and I call this y. How would you go from 10 to y? What would you have to do to go from 10 to y? Well, that would have to be 10 times 3 halves. Now I'm getting bigger. So I'd have to multiply by 3 halves. Or you could set up another ratio. Doesn't matter. Bottom line is you have to have ways to get x. And I know that you guys are going to figure that out. But we're moving on. The following rectangles are similar. Find the perimeter and area of each rectangle. So let's do that. First rectangle, the perimeter would be 2 plus 2 plus 3 plus 3, that's 10. The area would be 2 times 3, that's 6. Down here, the perimeter would be 10 plus 10 plus 15 plus 15, and that is 50. The area would be 10 times 15, and that's 150. So I want to establish three things. We're looking for a similarity ratio, we're looking for a perimeter ratio, and an area ratio. I want to talk about all three of these right now. The similarity ratio, you got to get this. That is the ratio of the corresponding sides or dimensions or measurements. Any corresponding measurements. For a circle, that'd be a radius. That could be a height. That could be a length. That could be a width. That could be a depth. Just any corresponding one-dimensional measurement. The perimeter is obviously the perimeter, area is obviously the area. So the similarity ratio is if you pick a corresponding measurement, the 2 and the 10 are corresponding, and that reduces to 1/5. Right now, the shape has a similarity ratio of 1 to 5. Right? 3 times 5 is 15, right? So it's the same in all those situations. The similarity ratio here is 1 to 5. What's the perimeter ratio? 10 and 50. Those are the perimeters. 10 to 50. What does that reduce to? 1/5. Similarity ratio and perimeter ratio are the exact same ratio. Why? Why does that work? Well, real quick, if we go here, look at those numbers. Could I factor out a 5 and say 2 plus 2 plus 3 plus 3? Well, what is 2 plus 2 plus 3 plus 3? Isn't that just this? So isn't it just 5 times the other perimeter? In other words, isn't it the same situation as the similarity ratio? Yes. But the area ratio is a little bit different. The area ratio is 6 to 150. Well, that's not 1/5. That's actually 1/25. Or you could think of it as 1 squared over 5 squared. Let's look at this real quick. 10, isn't that 2 times 5? 15, isn't that 3 times 5? If I reordered those numbers, isn't that 5 times 5 times 2 times 3? Or 5 squared times 2 times 3. 2 times 3 is the other area. So it's the original area times 5 squared, not times 5. So it's different because it's all multiplication. So here's one way I remember it. Perimeter is one-dimensional, right? If I put these in units, 2 units and 3 units, right? If I added 2 units plus 2 units plus 3 units plus 3 units, I would have 10 units. That is units to the first power. That is a one-dimensional measurement. Right? What is perimeter, guys? It's if you take the 4 sides and you made one big long line, the perimeter is the length of that long line. It is one dimension. It is length. But what about area? Area would be like 2u times 3u. That would be 6 units squared. That is two-dimensional. Area is a two-dimensional measurement, whereas perimeter is a one-dimensional measurement. So if you're solving for area, you have to use a two-dimensional ratio. In order to make it 2 dimensions, you have to square the ratio or the scale factor. It's got to be squared. So let's solve a problem. So here we have a rectangle, and they tell us that the length is 10 and the width is 8. We have a larger rectangle. I'm going to call it the width W and the length L. And they tell us that the similarity ratio is 2 to 3. So for every 2 we have over here, there's 3 on this one. So I'm going to do all my solving with ratios because that's what you're going to have to do this chapter. So let's get the length using ratios. Or you could use scale factor. I don't care. But I'm going to do it with some, actually I'll show you both. I'll do width both ways. If I'm using ratios, you would know that the ratio is 2 over 3. And it would have to be small over big for width. You would reduce 2 and 8 is 1/4. So W equals 12. If you were doing that with scale factor, you would do 8 times 3 halves to get bigger, and that would be 8 divided by 2 is 4 times 3 is 12. Works both ways. Okay, how about the length? Same ratio, 2 over 3 would equal 10 over the length. 2 and 10 is 1/5, so length equals 15 when you cross multiply. If you did it with scale factors, it would be 10 times 3/2. Well, 10 divided by 2 is 5, times 3 is 15. You get the same answer both ways. What about perimeter? This gets tricky. What is the perimeter of the first shape? It would be 36 when you add up all four sides. So let's find the new perimeter. I'm going to call it P. So it would be 36 over, let's put the ratio first. The ratio is still 2 to 3. Perimeter and the perimeter and the sides use the same ratio. That's a big deal. So 2 over 3 is still the ratio, and that would equal the small perimeter over the big perimeter. Well, 2 and 36 reduces to 1 and 18. 18 times 3 would be 30 plus 24. So this perimeter would be 54, which is the same thing as saying 36 times 3/2. That would be 36 divided by 2 is 18 times 3 is 54. So you can do it either way. All right. So now we're going to get a little bit messier. The area is 80. 8 times 10. So let's find the new area using our setups. It would be 2 squared over 3 squared. To work with area, you must square the ratio, equals 80 over A. Clean that up, that would be 4 over 9 equals 80 over A. If you don't square the ratio, it will not be correct. We're going to have to practice that a lot, but I showed you why earlier. It has to be this way. 4 and 80 reduces to 1 and 20, so the new area would be 180. If I was using scale factor, you would do 80 times 9/4. And that would equal 80 divided by 4 be 20, times 9 would be 180. So the new area is 180. You can verify it by doing 15 times 12. I promise you it has to be 180. You cannot do 80 times 3/2. It has to be 80 times 3 squared over 2 squared. It must be that way, or it doesn't work. So there would be all the pieces. All right. Another rule. Guys, we've already learned like 4. Let's keep going. There's a lot to learn. So this is the parallel line situation. So hopefully you were in class and you saw all this stuff, but just in case you weren't, parallel lines cut other lines proportionally over and over and over again. Every single combination of left over right must be the same ratio. That means that A divided by B must be equal to C over D, must be equal to E over F, must be equal to G over H, must be equal to I over J. All those must be the exact same ratio. But wait, it's actually any possible combination. I could do something like must be, let me restart this. What if I said something like G over C plus E? What would G over C plus E equal? Well, it would have to equal H over D plus F. Any combination of left over right has to have the same ratio. That's the rule. So what about all these? Those don't have to be the same ratio. It's the space between the parts, right? Like if you're a chef and you're cutting up things, as long as every cut is parallel, all of the pieces will be the same ratio. All the lefts over rights will be the same ratio. Any combination of left over right is the same ratio. But the actual knives that you're cutting with, the parallel lines, they don't have any of those same rules. So please don't do the same ratio with those parallel lines. The parallel lines themselves do not have this ratio. But the space between the parallel lines do. So this is the most, you will have a version of this picture more than any other. It's the most common one we're going to work with. So what are some proportions that are true here? Well, we have parallel lines. So let's start with what the parallel lines do for us. Any combination of left over right has to be the same ratio. That means that x over y has to equal w over z. That's the parallel line rule we just learned. And real quick timeout, remember every ratio or every proportion, there's 4 ways to do it. So you could have done x over w equals y over z, same thing. You could have done w over x equals z over y, same thing. And you could have done y over x equals z over w, same thing. How could you confirm that all of these are the same ratio? Or sorry, the same proportion? Look at the cross products. Every cross product is at xz and wy. Look at all 4 of them. Are they all xz and wy? Yes. That means they're all the same. They're all the same one. All right, so we got those covered. Some other things you could do. You could say something like w over x plus y. Sorry, not x plus y. That would not be a good example. W over x plus w. What would that equal? Well, it would equal the corresponding pieces z over z plus y. And just so we don't get too confused, it doesn't matter what order you put them in, but y plus z would be more consistent. There we go. Got it. But let's talk, so people are okay with that. This is where the problem happens. What if I said something like x over m? X over m. The most common wrong answer is w over n. No, 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 no. The parallel lines do not share the same properties as the other pieces do. So that's not going to cut it. If you're talking about the actual parallel lines, you have to focus on the triangles. There's a small, and we know they're similar because of AA, right? We have parallel lines, so we know they're similar. The triangles have sides of x, y, and m. The bigger triangle, how long is this entire side? It's x plus w. How long is this entire side? Y plus z, and the bottom is n. So I'm telling you, and we're going to work on this a lot, but if you're using the actual parallel lines, then you must focus on the entire triangle. It's the only way we can do anything. So what does x over m equal? It equals x plus w over n. That's the way it has to be. What if I said m over n? There's actually 2 answers. What would m over n equal? Look at the triangles. M over n would equal x over x plus w or y over y plus z. Y over y plus z. It's got to be the entire side. So guys, if you're using the actual parallel lines, you think about the triangles. So if I said m over n, that's the bottom of the small over the bottom of the big triangle. Equals x, small side, over x plus w, big side. Equals y, small side, over y plus z, big side. So what would be our setups here? First, let's use parallel lines. We know that 7 over 5 has to equal x over 4. Nothing reduces, so 5x equals 28. We know that x is 28 fifths. How about the other situation? What does y plus 2 have to go over? 12. Well, that is the parallel lines. If you're using the actual parallel lines, you got to look at the triangle. So if you were to redraw the 2 triangles, you have 7, 5, and y plus 2. That's the small one. The big one, we have x plus 7, 4 plus 5, which is 9, and 12. So if I do y plus 2 over 12, can I do 5 over 9? Yes. If I do the small over the big, I have to do the small over the big. The big, the whole thing is 9. There's no 9. There is a 9. 5 plus 4 is 9. You have to look at the triangles. Here, reduce 9 and 12 reduces to 3 and 4. So you cross multiply. That would be 3y plus 6 equals 20. 3y equals 14. Y equals 14 thirds. Same situation. 2 setups. First setup I'm going to do is y minus 2 over 12. What would that equal? Well, there's an x plus y there. I'm going to leave that alone. but that's bottom over bottom. That's small over big. So I'm going to go small 21 over big 35. No, 35. Yes, there's a 35. The whole thing is 35. You've got to look at the whole triangle. Anytime you're using the actual parallel lines, you have to do the whole triangle. So I'm going to solve this. So 21 over 35 is 3/5. Cross multiply, we get 5y minus 10 equals 36. And just so you know, I'm doing 5 times y minus 2. 5 times y minus 2 when I cross multiply here. Equals 12 times 3. So 5y equals 46. So y equals 46/5. Okay, got it. The next proportion, I can use just the parallel lines. I can say 21 over 24 equals 14 over x plus y. And I can do that because those are the spaces between the parallel lines. So I can use the parallel line property there. So let's solve this. 21 and 24. That would be 7 and 8. And then over here, 7 and 14. That'd be 1 and 2. Cross multiply, well, x plus y times 1 is just x plus y. 8 times 2 is 16. But we know what y is. Y is 46/5. So subtract the 46/5. 16 times 5 is 80. 80 minus 46 is 34/5. So those would be your two answers. We're moving on. We're going to practice that more, I promise. Angle bisector proportions. This one's not real intuitive. That means it's not something you can really figure out just by kind of looking. Well, actually, it is exactly what it looks like. I shouldn't say it that way. But it has nothing to do with similar triangles per se. Like there's no similar triangles in this picture. So people that forget the rule, they always try to figure it out using similar shapes. Well, that's not really possible to do. This is one of those situations where you kind of just have to know the rule. And the rule says that the two sides of the angle being bisected have the same ratio as the two parts of the third side. On this picture, what does that mean? That means that the two sides of the angle being bisected, 17 and 34, have the same ratio as the two parts of the third side. That's it. 17 and 34 reduces to 1/2. So 2a equals 21. A equals 21 halves. Side over side equals part over part. You just have to know the rule. We won't practice it a lot, but you be ready for it when it comes up. Here's another parallel line situation. Call this x. Are these the spaces between parallel lines? 16 over 15 equals x over 18. Yuppers. Reduce horizontally. That would be 3 times 5 and 3 times 6. So 5x equals 60 plus 36. That'd be 96. So x would equal 96/5. There we go. That's all there is to it. Easy breezy. Okay, we did this earlier. Angles of a triangle have that ratio. So you slap an x on it, and you solve. This would be 11x equals 180. So x equals 180 over 11. So the angles would be 2 times 180 over 11, which is 360 over 11. It would be 3 times that, which would be 540 over 11. I don't want to work it all out. And then 6 times that, 600 plus 480 would be 1080 over 11. Those would be the original sizes. How about here? It's a quadrilateral, and these are the side lengths. It's not angles. The angles would add up to 360, but what do the sides add up to? Well, whatever the perimeter is. So you would do 3x plus 3x plus 5x plus 6x has to equal the perimeter. So we talked about extended ratios at the beginning. We're unreducing them. In order to unreduce them, we have to slap an x on each one. So that would be 17x equals 201. I'm going to cheat a little bit, use my calculator. 201 divided by 17 does not reduce. Okay, so it's 201 over 17. Find the length of each side. You just multiply it back in. I don't want to do that, but you would do 3 times that, 3 times that, 5 times that, 6 times that. Two cylinders are similar. Their radius the radius of one cylinder is 10, the radius of the other is 25. So you don't have to draw it out, but the radius is 10, the radius is 25, so that means that the similarity ratio is 10 over 25, which reduces to 2/5. So that's the similarity ratio. But we're working with what? Area. So what is the area ratio? It's 2 squared to 5 squared, which is 4/9. So in order to do the area, we would have to use 4/9. It says the larger cylinder is 225. So 4 over 9 is small over big, right? 4 is smaller than 9, so small over big. Has to equal the small area, which we don't know, over the big area, which is 225. What did I do? Nope. Guys, that's pretty embarrassing. It's not 4 over 9. What does it equal? 2 squared is 4. 5 squared is 25. Why did I say 9? There we go. I was like, I did this problem earlier. I know that's not it. Got it. All right, we reduce horizontally. That's 1. I went ahead. I was jumping ahead. There's the 9. 1/9. So the area of the smaller one would be 36. If you don't square the ratio, you can't work with area. I talked about that earlier. You got to get used to it. Working with area, you must square your ratios. We're going to save that for another time. All right, guys. Have fun.